Welcome to this problem walkthrough. In this session, we'll be tackling LeetCode problem number 1390, titled 4 Divisors. This is an interesting mathematical problem that challenges us to analyze numbers based on their divisors. Stick around as we break it down step by step and explore efficient solutions. In this problem, we are tasked with finding the sum of all divisors of numbers in an array, but with a specific condition: the number must have exactly 4 divisors. If no such numbers exist in the array, the result should be 0. To clarify, a divisor of a number is any integer that divides the number evenly, leaving no remainder. For example, the divisors of 6 are 1, 2, 3, and 6, because each of these divides 6 without leaving a remainder. However, for this problem, we are only interested in numbers that have precisely 4 such divisors. The input is an array of integers, and the constraints ensure that the size of the array can be up to 10,000, and the values in the array can be as large as 100,000. Our goal is to compute the sum of divisors for numbers that meet this condition and return it, or return 0 if none qualify. Let's examine the first example to understand the problem better. Here, the input array is 21, 4, 7. For the number 21, its divisors are 1, 3, 7, and 21, giving it exactly 4 divisors. The sum of these divisors is 1 plus 3 plus 7 plus 21, which equals 32. For the number 4, the divisors are 1, 2, and 4, meaning it has only 3 divisors, so it does not meet the criteria. Similarly, for the number 7, the divisors are 1 and 7, so it also fails to qualify because it has only 2 divisors. Since only 21 meets the condition, the output for this example is 32. In the second example, the input is 12, 28, 30. For the number 12, its divisors are 1, 2, 3, 4, 6, and 12, which is a total of 6 divisors. This exceeds the requirement of exactly 4, so 12 is not included. For the number 28, the divisors are 1, 2, 4, 7, 14, and 28, which also gives 6 divisors, disqualifying it as well. Lastly, the number 30 has 8 divisors, 1, 2, 3, 5, 6, 10, 15, and 30, so it does not meet the condition either. Since none of the numbers in this array have exactly 4 divisors, the output is 0. Now let's consider a third example with the input 6, 10, 15. For the number 6, the divisors are 1, 2, 3, and 6, which gives exactly 4 divisors. However, the explanation mentions that the sum of these divisors is not explicitly requested in this specific example, which is an important point to keep in mind. For the remaining numbers, 10 and 15, their divisors do not meet the condition of exactly 4 divisors. This highlights the importance of focusing on numbers that qualify based on the divisor count and computing the sum only when applicable. The output for this example is 0. Finally, let's discuss the constraints and edge cases that must be considered. The constraints specify that the input array can contain up to 10,000 elements, with values as large as 100,000. This means that the solution must be efficient, as iterating through all potential divisors for every number in a large array could become computationally expensive. For edge cases, consider the smallest input, such as an array containing only the number 1, which has only one divisor and therefore results in an output of 0. Another case is when all numbers in the array have more than 4 divisors, resulting in no qualifying numbers and an output of 0. Conversely, if all numbers have exactly 4 divisors, their sums would be added together. The algorithm must handle these scenarios efficiently, even for the largest possible inputs. To solve the problem of finding numbers in the array that have exactly 4 divisors, the first approach we considered was a brute force method. The idea here is straightforward. For each number in the array, we count all of its divisors by iterating from 1 to the number itself. If the number has exactly 4 divisors, we sum them and include that sum in our result. The steps are simple: loop over each number, check which values divide the number, and collect those divisors. If the total count of divisors equals 4, their sum is added to the final result. However, while this approach is easy to understand, it is computationally expensive. For a number n, checking all divisors takes n time, and doing this for all numbers in the array results in an overall time complexity of k*n_max, where k is the size of the array and n_max is the largest number in it. This inefficiency makes the brute force approach unsuitable for large inputs, as it would likely exceed the time limit for competitive programming constraints. To improve upon the brute force approach, we can optimize it by iterating only up to the square root of each number instead of iterating all the way up to the number itself. The key observation here is that divisors occur in pairs. For example, if I divides a number n, then n/i is also a divisor. So, by iterating only up to sqrt n, we can find all divisors more efficiently. For each number, we track the divisors we find and their sum. If the total count of divisors is exactly 4, we add the sum of those divisors to our result. This optimization reduces the time spent checking divisors for a single number to O, sqrt, n, which gives us an overall complexity of O, k sqrt, n max, for the entire array. This approach strikes a balance between performance and simplicity, allowing us to handle moderately large inputs without exceeding time limits. However, it still may not be ideal for very large arrays or numbers with many divisors. To achieve even greater efficiency, we can use an optimized approach that leverages mathematical properties of numbers with exactly 4 divisors. Specifically, a number can have exactly 4 divisors in 2 cases: either it is the product of 2 distinct prime numbers, or it is the cube of a single prime number. For example, the number 6 is the product of 2 and 3, and its divisors are 1, 2, 3, and 6. Similarly, the number 8 is the cube of 2, with divisors 1, 2, 4, and 8. Using this insight, we can pre-compute all prime numbers up to the largest possible value in the input using the sieve of Eratosthenes. Then, for each number in the array, we check if it satisfies one of these 2 conditions. If it does, we compute the sum of its divisors and include it in the result. This approach is highly efficient because the sieve allows us to perform prime factorization quickly. The overall complexity is O, n plus k, where n is the size of the sieve and k is the size of the input array. While this method is the fastest, it is also more complex to implement compared to the brute force methods. For this problem, we chose the optimized brute force approach, which involves iterating up to the square root of each number. This strategy provides a good balance between simplicity and efficiency. It avoids the inefficiency of the basic brute force method while being much easier to implement than the mathematical property-based approach. The trade-off here is that while the mathematical approach is faster for very large inputs, the optimized brute force method is sufficient for most practical cases and avoids the additional complexity of pre-computing primes. With a time complexity of O, k sqrt, n max, the chosen strategy ensures correctness, maintains reasonable performance, and is straightforward to implement within typical competitive programming constraints. To solve this problem, we need to calculate the sum of all divisors for numbers in the array nums that have exactly 4 divisors. First, let's break down the condition. For a number to have exactly 4 divisors, it must satisfy 2 criteria: it always has the pair of divisors 1 and the number itself, and it must have one additional distinct pair of divisors, say a and b, such that a*b equals n. This means the total divisor count must equal 4, and we need to track and sum these divisors. The algorithm begins by iterating through each number in the array. For every number, we initialize 2 variables, divisor_count to count the total divisors and divisor_sum to keep track of their sum. These variables will help us determine which numbers meet the condition and contribute to the final result. Now, to check the divisors of a number efficiently, we don't need to iterate through all numbers up to n. Instead, we only iterate up to the square root of n. For each number I in this range, if I divides n evenly, i.e., n% I equals 0, we have found a divisor. We then add I to the divisor_sum. Additionally, if I is distinct from n/i, we add n/i to the divisor_sum as well. Each time we find a divisor, we increment the divisor_count. If at any point during this process the divisor_count exceeds 4, we can stop further checks early since the number no longer meets the criteria. Once all potential divisors have been checked, we validate the condition. If the divisor_count equals 4, we add divisor_sum to the global total. If not, we discard the number and move to the next one. Finally, after processing all numbers in the array, the function returns the total sum of valid divisors. There are a few key insights that make this algorithm efficient and robust. First, the optimization of divisor calculation allows us to only check up to the square root of n, which reduces the complexity significantly. Instead of iterating up to n, this approach minimizes redundant calculations by leveraging the fact that divisors come in pairs. Additionally, the use of early termination is crucial. If the divisor underscore count exceeds 4 during iteration, we can immediately stop further checks for that number, saving both time and unnecessary computations. It's also important to handle edge cases. For example, small numbers like 1 are ignored since they don't have exactly 4 divisors. Perfect squares, such as 16, require special attention because their square root contributes as a single divisor. Duplicate numbers in the input array don't pose a problem since each number is processed independently. The algorithm only relies on basic variables like divisor underscore count, divisor underscore sum, and a global accumulator for the result, ensuring minimal use of memory. Analyzing the complexity, the time complexity of this algorithm is determined by the iteration over nums and the divisor checks for each number. For every number n, we iterate up to sqrt n to find its divisors. This makes the total complexity O, k asterisk sqrt m, where k is the number of elements in nums and m is the largest number in the array. In terms of space complexity, the algorithm is very efficient, using only O1 additional space. It operates directly on the input and relies on a constant number of variables. Let's walk through an example to better understand the process. Consider the input nums equals 21, 4, 7, 10. We'll examine each number to see how the algorithm identifies valid numbers and computes their divisor sums. For the input nums equals 21, 4, 7, 10, let's evaluate each number. Starting with 21, its divisors are 1, 3, 7, 21. Since the divisor underscore count is exactly 4, we calculate the divisor underscore sum as 1 plus 3 plus 7 plus 21 equals 32 and add this to the global sum. Next, for 4, the divisors are 1, 2, 4, resulting in a divisor underscore count of 3. Since this does not meet the condition of exactly 4 divisors, we ignore it. For 7, the divisors are 1, 7, giving a divisor underscore count of 2, so it is also ignored. Finally, for 10, the divisors are 1, 2, 5, 10. The divisor underscore count is 4, and the divisor underscore sum is 1 plus 2 plus 5 plus 10 equals 18. Adding this to the global sum, we now have 32 plus 18. The final total is 50. In conclusion, the algorithm successfully computes the sum of divisors for numbers with exactly 4 divisors. For the given input nums equals 21, 4, 7, 10, the result is 50. This approach is efficient, leveraging optimizations like early termination and square root iteration, while also handling edge cases seamlessly. The final output demonstrates the correctness and efficiency of the solution. This solution implements the function sum4divisors to solve the problem of summing up all divisors of numbers in the array nums that have exactly 4 divisors. The main steps are: 1. Define a helper function get underscore divisors underscore sum n to calculate the sum of divisors for a given number n if it has exactly 4 divisors. This function uses a set to store divisors to avoid duplicates and iterates up to the square root of n to check divisibility efficiently. If the number of divisors exceeds 4 during the process, it exits early and returns 0. 2. Use the helper function to process each number in the input list nums. For each number, call get underscore divisors underscore sum to compute the sum of divisors if the number has exactly 4 divisors. The result is added to the total sum. 3. Finally, return the total sum of all valid divisor sums. The algorithm is efficient due to the square root iteration for divisor checks and the early exit condition when more than 4 divisors are detected. This ensures the solution handles larger input sizes within reasonable time limits. Here, we begin our Java implementation of the problem. The main function, sum4divisors, takes an array of integers as input and calculates the total sum of all numbers in the array that have exactly 4 divisors. First, we initialize a variable, total, to accumulate the sum. Then, we iterate through each number in the given array and call the helper function getDivisorSum for each number. This helper function determines whether the number has exactly 4 divisors and, if so, returns the sum of those divisors. The result of getDivisorSum is added to the total. Finally, the total sum is returned. Now, let's take a closer look at the getDivisorSum function, where the core logic resides. The getDivisorSum function is designed to identify the divisors of a number and check if there are exactly 4 of them. It uses a hash set to store the divisors, ensuring that each divisor is counted only once. The for loop iterates from 1 to the square root of the number, and for each divisor found, both the divisor and its complementary pair are added to the set. If at any point the size of the set exceeds 4, we immediately return 0, as the number does not meet the requirement. After the loop, we verify if the set contains precisely 4 elements. If it does, we calculate the sum of the divisors using a stream operation and return the result. Otherwise, we return 0, indicating that the number does not have exactly 4 divisors. This approach ensures efficiency by exiting early when more than 4 divisors are detected. In this problem, we are tasked with finding numbers in a given list that have exactly 4 divisors, and then summing up all such divisors. For instance, if the input list is 21, we need to determine if 21 has exactly 4 divisors, and if so, compute their sum. To solve this, we initialize nums as our input list in total to 0, which will store the cumulative sum of divisors for all valid numbers. We then process each number individually by calling a helper function, get_divisors_sum, which will calculate the sum of divisors for numbers meeting the criteria. For 21, we start by initializing an empty set called divisors to store its distinct divisors as we find them during the computation. To find the divisors of 21, we loop through integers from 1 to the square root of 21. For each integer, we check if it divides 21 evenly. If it does, both the integer and its corresponding quotient are added to the divisors set. For example, 1 divides 21, so both 1 and 21 are added. Next, we skip 2, since 21 is not divisible by it. For 3, we add both 3 and 7, as 21 divided by 3 equals 7. We continue this process until we exceed the square root of 21. Once the loop ends, the divisors set contains 1, 3, 7, 21. We then check if the set has exactly 4 elements. Since it does, we calculate their sum, 1 plus 3 plus 7 plus 21 equals 32. This value is returned to the main function, where it is added to the total, updating total to 32. Finally, since there are no more numbers to process in nums, we return the total, which is 32. Now let's consider a new example with nums equals 10, 15. We start by initializing total to 0. First, we process the number 10. We call get_divisors_sum to find its divisors. Inside this function, we loop through potential divisors from 1 to the square root of 10. For I equals 1, we add 1 and 10 to the divisors set. For I equals 2, we add 2 and 5, as 10 divided by 2 equals 5. We stop the loop once we exceed the square root of 10. The divisors set now contains 1, 2, 5, 10. Since it has exactly 4 elements, we calculate their sum, 1 plus 2 plus 5 plus 10 equals 18. This value is added to total, updating it to 18. Next, we move on to the number 15. Again, we call get_divisors_sum to determine its divisors. Starting with I equals 1, we add both 1 and 15 to the set. For I equals 2, we skip it since 15 is not divisible by 2. For I equals 3, we add both 3 and 5, since 15 divided by 3 equals 5. The loop ends as we surpass the square root of 15. The divisors set is now 1, 3, 5, 15, and it contains exactly 4 elements. We calculate their sum, 1 plus 3 plus 5 plus 15 equals 24. Adding this to the current total updates it to 42. With no more numbers in nums, we return the total, which is 42. In this example, the input list is nums equals 8, 16, and we initialize total to 0. First, we process the number 8 by calling get_divisors_sum. We iterate through possible divisors up to the square root of 8. For I equals 1, we add 1 and 8. For I equals 2, we add 2 and 4, since 8 divided by 2 equals 4. The loop ends here, leaving the divisors set as 1, 2, 4, 8. With exactly 4 divisors, we calculate their sum, 1 plus 2 plus 4 plus 8 equals 15. Adding this to total updates it to 15. Now we process the number 16. Calling get_divisors_sum, we check divisors up to the square root of 16. For I equals 1, we add 1 in 16. For I equals 2, we add 2 in 8. We skip I equals 3 since 16 is not divisible by it. For I equals 4, we add just 4 because its quotient is already in the set. At this point, the divisor set is 1, 2, 4, 8, 16, containing 5 elements. Since it does not meet the requirement of exactly 4 divisors, we ignore this number and return 0. The total remains 15, which we return as the final result. This example highlights the efficiency of the algorithm in handling numbers with more than or fewer than 4 divisors, ensuring only valid numbers contribute to the sum. Here, we begin by analyzing the time complexity of the solution. The first component is the outer loop, which iterates over each number in the input list nums. If the list contains m elements, this contributes O(m) to the overall complexity. Next, we have the inner function, get_divisors_sum, which is responsible for calculating the divisors of a given number n. To do this, it iterates from 1 to the square root of n. For each divisor found, it performs constant time operations like adding to a set or checking the set size. These steps are repeated for up to sqrt n divisors, so the inner loop has a complexity of O sqrt n. Additionally, the early exit condition, which stops further iterations once the number of divisors exceeds 4, helps reduce computation in many cases. However, in the worst case, such as when a number has 4 or fewer divisors, the loop will still run O sqrt n iterations. Now looking at the total time complexity, we combine the contributions from the outer loop and the inner function. In the worst case, the solution runs in O(m** sqrt max_n, where max_n is the largest number in the input list nums. For the average case, the complexity depends on the distribution of numbers in nums. Smaller numbers or those with fewer divisors often result in fewer iterations, making the complexity sublinear with respect to sqrt max_n. Shifting to space complexity, the main factor here is the divisors set, which stores all divisors of the current number. Theoretically, a number can have up to O sqrt n divisors, but the early exit optimization ensures that the set size never exceeds 5 elements, 4 valid divisors plus 1 extra check. This effectively bounds the space usage of the set. Beyond this, the solution uses a few auxiliary variables, like total and I, which require constant space. Therefore, each of these components contributes to an overall space complexity of O(1). In total, the space complexity of the solution remains O(1), thanks to the constant bound size of the divisors set and the limited usage of auxiliary variables. To put this into perspective, let's compare this with a brute force approach. In a naive method, we might iterate over all integers from 1 to n to find all divisors, leading to an O(m** complexity for the entire input list. The current solution, however, improves upon this by leveraging the mathematical property that divisors come in pairs, reducing the inner loop complexity to O sqrt n. Additionally, the early exit condition prevents unnecessary iterations for numbers with more than 4 divisors, further enhancing efficiency. These optimizations make the solution significantly faster and more practical compared to the brute force approach, especially when dealing with larger input sizes. Let's break down the analysis into best, worst, and average cases. In the best case scenario, if all numbers in nums have fewer than 4 divisors, the early exit will trigger frequently, allowing the inner loop to terminate quickly. This reduces the total complexity to approximately O(m), as the computation per number becomes minimal. In the worst case, however, if all numbers have exactly 4 divisors or fewer, the inner loop will perform O sqrt n iterations for each number. This results in a total time complexity of O(m** sqrt max_n. For the average case, real-world datasets often include numbers with a mix of divisor counts, and most numbers tend to have relatively few divisors. This means that the early exit optimization will still apply in many situations, and the solution will frequently run faster than the worst-case bound, typically achieving a sublinear complexity in terms of O sqrt max_n. When working on this problem, there are a few common mistakes to avoid. First, many people write inefficient divisor counting logic by iterating from 1 all the way to the number itself. This approach works but is slow for larger inputs. Instead, leverage the property that divisors come in pairs, meaning if D is a divisor of n, then n/D is also a divisor. This allows you to only check up to the square root of the number. Another common error is failing to handle edge cases. For instance, the number 1 has only one divisor, prime numbers always have exactly 2 divisors, and squares of primes, like 49, have exactly 3 divisors. Missing these cases can result in incorrect outputs. Additionally, avoid summing the divisors of a number prematurely. If the count of divisors isn't exactly 4, the sum doesn't matter, so compute the count first to save time. Finally, if you're processing multiple numbers, calculating divisors naively for each one can be very inefficient. Instead, consider pre-computing divisor counts for all numbers up to the maximum value in the input using a sieve-like approach to avoid redundant computations. Another mistake to be mindful of, especially in interviews, is ignoring time complexity. While a brute force solution might seem straightforward, failing to optimize it can be a red flag. For example, the naive approach might run in O, n *sqrt, max, nums, but this can be improved significantly with techniques like pre-computing divisors. During interviews, always discuss the trade-offs and optimizations you can make. One key insight is recognizing that numbers with exactly 4 divisors follow a specific pattern. They are either the product of 2 distinct primes, like 6, or the cube of a prime, such as 8. By identifying this pattern, you can refine your divisor checking logic. Interviewers also look for how well you balance efficiency and simplicity. You could pre-compute results for faster lookups, which is great for large datasets but uses more space. Alternatively, you could calculate divisors dynamically, which conserves space but may be slower for larger inputs. Discussing these trade-offs shows your ability to think critically about problem solving. When explaining your solution, it's important to clearly articulate the properties of divisors and how your optimizations reduce computational complexity. Clear communication is just as important as getting the correct answer, as it demonstrates your understanding of the problem to the interviewer. For additional practice, some related problems can help reinforce the concepts. For example, LeetCode 263, ugly number, also involves verifying numbers based on their divisors, while LeetCode 507, perfect number, focuses on summing divisors under a different condition. LeetCode 204, count primes, introduces the sieve of Eratosthenes, which parallels the idea of pre-computing results for efficiency. Finally, LeetCode 172, factorial trailing zeros, involves analyzing factors and divisors, with a specific focus on powers of 5. These problems can help you build a strong foundation in divisor-related logic and optimization techniques. There are multiple approaches to solving this problem, each with its own trade-offs. The brute force approach is the simplest. It involves iterating through all numbers from 1 to n, counting divisors, and summing them if exactly 4 are found. However, this approach is inefficient for large inputs, as its time complexity is O, n *sqrt, n. A more efficient option is the divisor pair optimization, where you count divisors only up to the square root of the number and use divisor pairs to reduce iterations. This method has a time complexity of O, sqrt, n, for a single number but requires careful implementation to avoid double counting divisors. For even better performance on multiple queries, you can use a sieve-like approach to pre-compute divisor counts and sums for all numbers up to the maximum value in the input. While this reduces redundant calculations, it increases space usage. Lastly, you can use prime factorization to check if a number is the product of 2 distinct primes or the cube of a prime. This approach is highly efficient but requires pre-computing primes, which can be less intuitive for beginners. Choosing the right approach depends on the constraints and input size, and discussing these trade-offs demonstrates a strong grasp of problem-solving strategies. Great job! To wrap up, we reviewed the solution for the 4 divisors problem, summarized the key steps, and highlighted important takeaways. Keep practicing and exploring similar problems to sharpen your skills. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!